In this experiment, we're going to be drawing Lewis dot structures and determining their polarity and geometry. So you've probably been doing this in lecture at this point. A Lewis dot structure is a structure that shows how the atoms are connected. It shows all of the valence electrons, only valence electrons. It shows what we call lone pairs that are not bonding to, not being shared with something else. And remember that a dash is actually a pair of electrons. This is a bonding pair. Of electrons. Also, I didn't show it this way, but they can be shown with the bonds. I don't usually do this, but it's fine, and that's what it means using those dashes. Okay, we also say electron groups a lot. A group is any electrons that are kind of together because they're being shared, or a lone pair. So, for example, and this is a good way to put it, this bond could be any type of bond. It could be single, triple, double. So, for example, in this molecule, it has 3 electron groups. Isomers are different compounds, but they have all the same atoms. They're just connected in a different way. We would say that they have the same, or that they have different skeletons with all of the same atoms. And I'll do an example in a second. Isomerism is when you have that possibility of more than one structure with all of the same atoms. Typically, isomers are organic compounds, carbon-based compounds. Okay, so let's look at one example. And, you know, in this class, it's general chemistry. We usually don't try to make you come up with all the combinations of this. It's really organic chemistry. So we do a lot of examples, and in the lab, we will have these molecules set out. Anytime for a particular formula, you see 2 models, 2 molecular models, that means you have isomers. So this one, I'm just going to draw it really quick. The other one we could do is to have 1 fluorine on each of the carbons. And if we were to name this, we would call it a 1,2 difluoroisomer. Again, we're numbering this way. So those are 2 isomers. You might wonder, well, what if we put them both on the second? And then you want to say that it's a 2,2 difluoro. But the thing is, if we have this molecule, this would be carbon number 1, because when we number them, we number from the most interesting end. We would number from an end that has something other than hydrogen, and not to get too complicated, but that is the 1,1 again. So both of the fluorines are on the end. This one has 1 on each. So there are 2 isomers of the C2H4F2. Okay. Now about polarity. Polarity depends on having a polar bond and asymmetry. So for example, and let me talk about polar bond real fast. We are using a really simplified definition of polar because there really is some gray area there. We're going to call something polar if there are 2 different elements bonded together. In other words, this is nonpolar. This one is polar. And we're also going to consider C to H as non. It's kind of an exception, and it's important because that bond is probably one of the most common bonds in the world, actually, because of organic chemistry. But anyway, so know those rules, and then when you look at the molecule, you need to see if it is symmetric or not. So for example, if the compound, and you have to think about 3D, so drawing a 3D tetrahedral compound, let me draw that like this. This is how we would draw a tetrahedral compound. Showing the 3D, the line is on the screen, this line is on the screen, this one points out toward you, this one goes back behind the screen. If you remember, tetrahedral has kind of this triangular base, and then it has one pointing up. That's what I'm looking at. Those three at the bottom would be on the floor, so to speak. So to draw the rest of this molecule, let's just say I had fluorine at all 4 places. These are polar bonds, but this would be nonpolar. Let me go over here. If I had just one fluorine and these hydrogens, then I do have a polar bond, and it's not balanced by, these are all nonpolar, it's not balanced. And so I would say this has a net polarity going up. Fluorine is much more electronegative. It's further up and to the right on the periodic table. So that is going to have, this end is going to be kind of negative, and this end will be kind of positive. So this is definitely polar. And if I did just one thing, and I'm not going to draw the whole molecule, but let's just say I did this and it had hydrogens in all places. Again, that would be non, because carbon to hydrogen is nonpolar, and also that's really symmetric. Okay, so a polar molecule, you're looking at the net polarity. Let's look at these up here and say whether they're polar or not. And the thing you have to know, and I told you this before, single bonds rotate. And so that can affect the polarity. And I'm just going to draw one of these in one carbon in 3D. Again, dashed line is behind the screen. Well, I'm going to draw this one too. Let's see. Okay, on the 1, 1, both of these are on the same end, so the polarity would point toward them. But the thing is, remember that this is rotating constantly, and so those 3 atoms on this side are constantly changing positions. The net polarity on this end would be straight out. So this one is definitely polar. Okay. On this other one, it has, I'm just going to draw them at different places. It has a fluorine on each one. Remember that this is rotating, which means that these are rotating, changing the position from top to out to bottom. And so the net polarity on this fluorine is not straight down because it's rotating. The net polarity for this one is straight this way. And the polarity on this one, because this is rotating, is straight this way. And so they look like they cancel. Now, I'm not going to tell you this is a perfectly nonpolar, but for a kind of simplified way of looking at it, it is nonpolar because they are opposing each other. What I'm trying to say is, I'm giving a disclaimer, there are more complicated factors that can come into effect that you'll learn in organic chemistry. Okay, let's start another video.